Okay, since it's 3 o'clock, I'm going to start. Let's recall what we did last time. It was something purely algebraic, right? By which I mean it was something applicable for all fields. The fields were not special, like the field of rational numbers or QP or K power series T. It was a general field. So that's what we did last time. K is any field and P is a prime number. And we were interested in classifying cyclic extensions of K of degree P. What are they equal to? That means we want to parameterize them by a set which is easier to compute, which we can explicitly find out what it is, right? So there were two cases which we distinguished. The first case is when the characteristic of the field K is equal to the prime number P. And the second case is the one where this characteristic is different from the prime number P. And we saw that in this case, when the characteristic is equal to P, the set of cyclic extensions is in bijection. There's a natural bijection, right? With the set of FP lines in K plus modulo PK plus, where P is this endomorphism of K plus, which sends x to the P minus x. And what is the bijection? For example, let me give the map in this direction. If I have a line D, here it's taken to the extension. To K, you adjoin the roots, pth roots, I mean this P being curly P. P, this stands for all x such that P of x is in D. Similarly, when the characteristic is different from P, in this case, it was slightly more complicated. First of all, from K, you have to pass to the field K prime, which is obtained from K by adjoining a primitive pth root of unity, zeta. So K prime is K zeta, where zeta to the power P is 1, but zeta is different from 1. This is always a Galois extension. And if I denote by delta the Galois group, then there is this injective, I mean, it comes with an inclusion, which is called the cyclotomic character, into FP star. In particular, this delta is cyclic of order dividing P minus 1. Right? Okay. So from K, you have to go to K prime, and then you have to look at K prime modulo K prime star, modulo K prime star pth powers. This group, of course, comes with an action of delta. What does delta act on? Delta acts on K star, of course, on K star, the multiplicative group, and on this quotient of the multiplicative group, K prime star pth powers. So we are looking at this is an FP space. This any commutative group, suppose you write it additively, then M plus PM, that's an FP space. But if you were to write it multiplicatively, then m modulo m to the power p, this is an FP space, right? This is, it's just a matter of notation. Okay, so you you have this FP space. Inside it are some lines. And there are lines which are delta stable, and though there are lines which are not delta stable. So the set of delta stable FP lines in this FP space, and moreover, the ones on which delta acts through omega. So if a group, I don't know, call it G, acts on an FP line D, then of course you get a character chi from G to FP star. FP star is here. And why do you get this character? Because this FP star is nothing but the group of automorphisms of D as a vector space over FP. Okay. Or the automorphisms of G just as a group. I mean, it comes to the same. So this is slightly more complicated. Things are easier if the characteristic is equal to P. Then you just have to look at FP lines in this space. But if the characteristic is different from P, then you need to adjoin a primitive pth root of unity to get a field K prime. And then you will look at K prime modulo pth powers, K prime star modulo pth powers, inside which you have to look at FP lines, and only those which are delta stable, where delta is this Galois group, and not just delta stable, but the ones on which delta acts through omega, where omega is a cyclotomic character, and this gives the action of delta on the pth roots of unity. So this is the omega gives the action of delta. Actually, the correct way of writing it is you have K star, K prime, you have K prime star, and the P torsion. So this is NFP line, NFP space of dimension 1. So the action of delta is given by some character, and that character is called omega, the cyclotomic character. Okay, so that's what we had done last time. And today, what we are going to do, we are going to do something more general. So we are given a field K and a prime P as before. That's what we were given here, a field K and a prime P. But now we are interested in all solvable degree P extensions and not just the cyclic ones. The cyclic ones are a very special case of solvable extensions. I'll define what solvable is, right? It was already done in the tutorial, but let me just recall that a solvable extension of a field is a separable extension, L over K, such that when you take the, for any separable extension, you can take the Galois closure. So let me call it L hat in this case. So when I take the Galois closure, I get a Galois group, the Galois group of L hat over K. And the requirement, the condition for the extension to be solvable is that this Galois group should be solvable, right? So easy example. Easy example. All separable cubic extensions are solvable in this sense. Of course, they need not be cyclic. They need not even be Galois, right? A cubic extension, for example, cube root of 2 over q. This is, of course, not even Galois. Forget about being cyclic, but it is solvable, because when I take the Galois closure, I get the group. This group is going to be S3, the symmetric group on 3 letters, which is solvable. So that's the notion of solvable extensions. So the aim today is to give a natural bijection. Just as there's this bijection, here it was this bijection, right? Between the set of cyclic extensions of degree p and some other set which is easier to construct, of which we a known set, whereas the set of cyclic extensions is an unknown set. And if you give a bijection of an unknown set with a known set, of course, we have determined what that unknown set is. So today, we are going to give a bijection of this unknown set of all soluble extensions of degree p of our field K with what? So that will take some explaining. I mean, I'll explain what with what. So that's the aim of today's lecture. Okay, so, but if I were to summarize what we are going to do, then here is a summary. Of course, from the set of all soluble extensions of degree P, you have a map to the set of all finite Galois extensions. You just take your soluble extension L and take its Galois closure, L hat. So that's going to be a finite extension of our field K. And of course, this is not a bijection. This is not a bijection. Far from it. I mean, in general, but what we will show us is that it's injective, and we will characterize the image. So instead of, suppose you have an unknown set. Unknown set. And you have a known set. Suppose you give, first of all, an injection. So you give two things. You give an injection and you characterize the image of that injection. Then, of course, you have determined what this unknown set is. So that's what we are going to do. This set of soluble extensions of degree P is unknown, and we want to parameterize it. So we first approximation of what the parameterization is to say that that taking the Galois closure is injective, and we will characterize the extensions which are obtained in this manner. Okay, so let's start. So there are some group theoretical preliminaries which were already started in the tutorial. Let me just recall them. Suppose you have prime number P, you have a group of order P, capital P is a group of order P. Then you can put this capital P inside SP, the symmetric group. This is what is this? S. This is S. And SP is the symmetric group on the set P. So normally you take the symmetric group on the set 1, 2, up to some n, and you call it Sn. People actually call it S with this kind of S. But obviously, you can take any set instead of this set. And my set happens to be the set P, which happens to be a group. But the advantage of this is that then I can think of P itself as a subgroup of SP, because P, natural inclusion, so left translations, right? Okay, and then I can speak of the normalizer of capital P inside SP. We always have a homomorphism from n modulo P to FP star. In general, if we have a group G and a subgroup H, well, of course, the subgroup has to be normal, right? So if you have a group G and a normal subgroup H, then we have the quotient G modulo H, and we always have a homomorphism from G modulo H to the group of automorphisms of H. Wait a moment, what am I saying? That seems to be, yeah, okay. Okay, at least if it's normal and commutative, right? Which is the case here. P is normal, and P is of course normal in N, and P is also commutative. So you get a map from N modulo P to FP star, which is to be thought of as the group of automorphisms of P. The group of automorphisms of P is FP star. Okay, so what does this equality actually mean? It means that I have a map from FP star to the group of automorphisms of P, which sends an element A to the map which takes x in P to x to the power A. And this is an isomorphism. So that's why we can identify aught P with FP star, and I write equality here. Okay, so the first lemma says that N modulo P to FP star, this is an isomorphism. This is a special case of the result which was proved for a general group G, finite group, in the tutorial, right? What was proved in the tutorial? That, if I have the special case of what was proved in the tutorial is that G commutative group, let's say finite commutative group, then you have G, you can think of it as, SG, and then when I determined N, the normalizer of G in SG, and when I proved that N modulo G is actually equal to aught G. So this was proved in the tutorial. And I'm just using the special case when this group G is equal to my group P, when G is cyclic of order, prime order P. Okay, but here is something which is special in this case of a prime index. Suppose I have a transitive subgroup of SP. SP is a symmetric group on P letters. This is a very special, very important proposition, and it was proved by Galva maybe when he was 16 years old. Or 18 years old, I don't know. But he was very young. 18 years, he established the whole of Galva theory. So maybe, yeah. So let's put 18 just in order to make sure that nobody objects. So when he was 18 years old, he not only, this is part of, see, he was looking at this problem of characterizing solvable extensions. Which are the extensions of a field which are solvable by radicals? Then he gave a criterion in terms of his Galva theory that an extension is solvable by radicals if and only if its Galva group is solvable. he defined what it means for a group to be solvable, right? And then proved that an extension is solvable by radicals if and only if the Galois group is solvable. I mean, I've sort of taken that as a definition just now. Okay. But then the next step for him was, okay, you have reduced the problem to saying which groups are solvable. Now you characterize those subgroups of the symmetric group which are solvable. Which ones are solvable? The Galois groups are always transitive. Huh? So you have to characterize transitive subgroups of SP which are solvable. And he did it for prime indices. He said a subgroup gamma of SP is solvable if and only if it contains a unique Sylow P subgroup. P being, of course, the same prime as this P here. So this was done in the tutorial last time. Okay, so but it's a very important result, and there's actually a generalization. I mean, there's something which comes next, but I won't go into it right now. This is what he did in his first memoir. Then there is a second memoir, and that's also very important, but this I'm not going to discuss. So the next proposition is also a very general result, very useful in various contexts. And it says that if I have a short exact sequence, this is, what is it called? A short exact sequence of finite groups. So C, gamma, and G are finite groups. C is actually a normal subgroup of gamma, and G is the quotient of gamma by C. That's what it means for it to be a short exact sequence. Now, I'm given a short exact sequence of finite groups, and I'm told that the order of the quotient and the order of the subgroup are relatively prime. The GCD is equal to 1. If so, then this sequence admits a section. So a section is a homomorphism from G to gamma, let's call it S, such that if I apply S first and then apply this pi, I get back the identity of G. So some short exact sequences admit sections. For example, if I take A3 sitting inside S3, and the quotient is Z mod 2Z, right? This admits sections. It admits some sections. Whereas if I have 0 going to Z mod 2Z, going to Z mod 4Z, here, of course, 1 will have to be sent to 2. And then Z mod 4Z, there's a natural map, which goes down to what? To Z mod 2Z. This is subjective. Here, X goes to X bar. So this does not admit a section, right? So some short exact sequences have sections and some don't, right? The theorem of Schur and Zassenhaus says that if it's a short exact sequence of finite groups, and if the order of the quotient is prime to the order of the subgroup, then there are always sections. And not only that, any two sections are conjugate by an element of C. So maybe this is elaborated here. Yeah, so it's explained here further. So what is a section? A section is a map from G to gamma. Map means a homomorphism of groups such that this composite is equal to the identity. And if I have one section S and I take an element gamma in the ambient group G is this group gamma. Gamma is the group in the middle. Little gamma is an element of the group capital gamma. And if I define S prime, define S prime to be for an element G of, so S prime is being defined as a map from G to gamma. So I have to say what S prime of G is, and I'm saying take it to be gamma SG gamma inverse, the conjugate of SG by the element gamma. Then I've defined this map S prime, right? And it is easy to check that this is also a section. Now, this is a very important, purely algebraic result. So very, okay, let me not keep on saying that it's very important. So we will prove it only in two special cases. This we will prove, no, not fully. So this we will give a sketch because it relies upon some theory, and yeah, this case we will give a full proof. So what are the two cases? The first case is when the subgroup C, C is the subgroup here. So the first special case is when this subgroup is commutative. And the second special case, which we will prove, is when C is a P group. A P group is a group of order P to the n for some prime P and some n. It's a group of P power order. So not only is C a P group, which may or may not be commutative, but the quotient G is cyclic. Of course, if I denote the order of the quotient by E, then P bar, the image of P in Z mod Ez, is going to be invertible because GCD of P and E is equal to 1. Okay. So let's start by and proving the special case 2. Proving meaning I'll not prove the entire thing, I'll show that a section always exists. So what is this special case? G is cyclic. So it is generated by S bar for some S in gamma, and the order of C is P to the n. And of course, P bar belongs to Z mod Ez star, and E is the order of G. So take S such that G is generated by S bar, the image of S, and the order of S bar is equal to E, right? Because it's a cyclic group, so the order of the generator is, of course, equal to the order of the group. Now, n is this exponent, right? P to the n is the order of G. I take capital N, I take it to be an integer bigger than n, little n, and such that P to the capital N, this power of P is congruent to 1 modulo E. You see? So that this P bar in Z mod Ez star, let's take some R to be the order of this P bar, and take N to be any multiple of R, which is any multiple of R, which is, I mean, this multiple should be greater than little n. That's what you need to, you just take. Then you'll have this, right? Now put t equal to s to the power p to the n. S is an element in gamma, and therefore t is, of course, also an element of gamma. What about t to the power e? So t to the power e is s to the power e times p to the n, but e times p to the n, little n, that is equal to the order of gamma. And e times p to the capital N is a multiple of e times p to the little n. So if it's a multiple of this, this is a multiple of the order of the group gamma to which this element S belongs, and therefore this whole thing has to be equal to 1, because this is a multiple of the order of the group gamma. How about T bar? What is it equal to? T bar is the image in G, which is gamma modulo C, right? T bar is equal to S bar, because T bar, T is S to the power P to the N. Normally, T bar will have to be equal to S bar to the power P to the power N, but P to the power N is congruent to 1 modulo E by construction. So this is equal to S bar, because this is equal to 1 modulo E. So T bar is equal to S bar because of this. And therefore, the order of T bar is equal to E, which is the order of S, right? And that's also the order of the group G. We are assuming that G is cyclic. Now, what do we know about T bar? We know that T bar to the power E is equal to 1. And we know that the order of T bar is equal to E. We know these two things. And these two things, of course, imply the order of T itself is equal to E. Order of T is equal to E. And then there's a unique map from G to gamma, which sends S to T. And that is a section. It's not difficult. It's really a very cute little exercise in group theory. What it is saying is that if you have a group, C is a P group, so gamma is a finite group, and C is a normal subgroup. So the hypotheses are the gamma is a finite group, C is a normal subgroup, C is a P group, and gamma modulo C is cyclic of order prime to P. These are the hypotheses. And the conclusion is that that this projection gamma to gamma modulo, gamma modulo C here, right? There's no G. That this projection, this admits a section. Just a moment. Hello. Namaste. Okay, so let's start. Yeah, that's what. This is the little group theoretical lemma, which is very important. Now, I said in the special case one, when the subgroup C is commutative, I'll give an idea of the proof. And here, I'll talk about not only the existence, but also the uniqueness of the section up to conjugacy. So this follows from a theory. And the theory, of course, we are not going to develop. So, but I'm going to tell you what that theory involves. And the theory is called Chromology of Groups. So that theory works whenever you have a group G, finite, not finite, and a commutative group C, and an action of G on C. So what is an action? It's just a homomorphism from the group G to OT C, where OT C, of course, is the group of automorphisms of the group C. So that's also called a G module. A G module is just a commutative group together with an action of G. So whenever you have a group G and a G module C, you get a sequence of other commutative groups called HI G with coefficients in C. These are called the Chromology groups of the G module C. For every index I, you have HIGC. So some of these, for I equal to at least 0, 1, 2, there are interpretations of these cohomology groups in terms of very concrete things. For example, for I equal to 0, H0 is simply C to the power G. It's not the set of all mappings from G to C. No, it is the fixed subgroup of C for the action of G. So it consists of not all C in G, but all C in C, such that, when C and I make the element G act on it, then I should get back C. And what is this notation? This notation is, you see, we are given an action of G on C. So theta is a map from homomorphism from G to OT C, and this GC, little c, is just theta of G. Now this is an automorphism of capital C, right? This, let me just make clear that on the left here, I have little c in G. So applied to little c. So that's an automorphism of capital C. So I can evaluate it at little c, and that is the notation G, C upper G, whatever. So that's what H0 is. There's an interpretation of H1 as well. H1 GC is the set of all C conjugacy classes of sections of this semi-direct product. The semi-direct product of G with the G module C. What is the semi-direct product? Let me quickly recall. So it consists of all pairs C, G, consists of all pairs C, G, where C is in capital C and little g is in capital G. And how do you multiply two such pairs? So C1, G1 times C2, G2 is C1, and then you multiply C1 not with C2. That would be the direct product of these two things. What we are doing is called the semi-direct product. So you multiply C1 not with C2, but C2 acted upon by G1. G1 is the one here. And the second component is just the product of G1 and G2. That's, you do nothing here. Only in the first component, you do something funny. So it's not C1, C2, it's C1 multiplied with G1 acting on C2. That's the first component. And then there's the second component, is just G1, G2. So the neutral element of this, as I said, so this H1 can be identified with the set of all conjugacy classes. And I also said that H1 or HI in general are groups. So each of them has to have a neutral element. So you can ask, what is the neutral element of H1? So the answer is that it is the section. If you identify H1 GC with sections up to some equivalence relation, you could ask then the neutral element here corresponds to the section G going to 1, G. That can be seen to be a section, of course, right? Here, S G going to 1, G is a section. Okay, so that is the interpretation of H1. And there's this H2, which classifies extensions of G by the G module C. Now, what does that mean? It means there are equivalence classes of this kind of short exact sequences where C is a subgroup and G is the quotient, such that the resulting conjugation action. So whenever I have a short exact sequence, I have an action of G on C. I have an action of the quotient on the subgroup. And that action should be the same as the given action. That's what H2 classifies. So in order to talk about H2 GC, you have to give an action of G on C. Once you have an action of G on C, you can talk about all short exact sequences. This kind of short exact sequences are also called extensions of G by the G module C. So H2 classifies extensions of G by the G module C. And the neutral element of this is this extension, which is the semi-direct product. This extension has a section, as I said, the section which sends little g to 1, little g. Moreover, in fact, one can see that an extension admits a section if and only if its action is isomorphic to the semi-direct product. So as far as this H2 is considered, an extension is trivial if it admits a section. Trivial means isomorphic to the semi-direct product. Given a group G and a G module C, there is of course always an extension of G by C, namely this semi-direct product. So if theta is the action of G on C, then C cross theta G is the notation for the semi-direct product. This extension of G by C is always there, and there may or may not be other extensions depending upon what G and C are. Okay, so that was a general theory. G was an arbitrary group, C was an arbitrary G module. Now, if G and C are finite, then these groups, HIs, are also finite. Okay, and they are finite for all I. There's something wrong with this. Moreover, if the orders of G and C are relatively prime, then these HIs are actually trivial for all I. Maybe not, or maybe I should write 1 here. Yeah. Now, as I said, H2 being 0 means that the only extension is a semi-direct product. And H1 being 0 means that any two sections are conjugate by an element of C. So that proves our theorem in this case 1, special case 1. What was the special case? When C is commutative. If C is commutative and I'm given this short exact sequence, I can make C into a G module because of this short exact sequence. And this sequence itself will be an element, something wrong today, will become an element of H2GC. But if these have relatively prime orders, then this is trivial. And therefore, this is the semi-direct product, and the semi-direct product always has sections. That's the first thing. The second thing is to say that any two sections are conjugate, and that is it's the same proof. Instead of H2, you now use H1, which classifies C conjugacy classes of sections, and H1 is trivial for the same reason that whenever these two are relatively prime, you see what happens is that these HI, why do they vanish when these things are relatively prime? Because the HI gets killed by the order of G as well as the order of C. Now, if some group H gets killed by some N and M, and M and N have GCD1, all this happens, then of course this H itself is the trivial group, right? Okay. Now, that was a special case when C was commutative, right? What happens if C is not commutative? So let me just say a word about, I mean, that's a purely algebraic thing, which we don't even need, but let me just say, because you might need it somewhere else. So let me say a word about what the proof is in that case. So the thing is that if one of C or G is solvable, then it follows from this case, which we already proved, by some sort of levisage. That's what the word is. But one step at a time, doing things one step at a time. Okay. And now there's a very deep theorem, which is due to Finite and Thompson, which says that if you have a group of odd order, then it's necessarily solvable. So you'll be back in this case if one of C or G is of odd order. But if the orders are relatively prime, then of course one has to have odd order. I mean, both of them cannot be of even order. So one of them is of odd order. Then by Finite and Thompson, it's solvable. But by this previous case, solvable groups are covered. So that's the general idea. Okay, now let's get back to some. Maybe I'll skip this because I'll do it next time. I think. Mode. Yeah, this is to be skipped. Let's come back to this problem that we are discussing. We have a field F. So I've been calling it K, but now let me call it F because K will be something else. So I have a field F and a prime P, which may or may not be equal to the characteristic of F. There's no relation between these two things. And as in the tutorial, I'll say that a finite extension is solvable if it is separable and the Galois group of E hat over E is a solvable group, where E hat is the Galois closure of E over F. And as I just gave a trivial example just now, that Q, I take Q, I take Q to which I join. Now something is not working properly today. I cube root of 2, then this is a solvable extension, right? It's not even Galois, but it's solvable according to this definition. It says that when I take the Galois closure, the group is going to be S3, and that's a solvable group, so this extension is solvable. Now here is a lemma, which says that suppose I have an extension of degree P, prime degree, which is solvable, then there exists a cyclic extension F prime of degree dividing P minus 1, such that two things happen. EF prime over F prime, there's a diagram here, yeah. So EF prime, so let me draw it here, so that what is given is F, this, and E. So this is given to me, this part is given to me, and I'm saying there exists an F prime. This is cyclic of degree dividing P minus 1, such that EF prime over F prime is cyclic. Of course, it's going to be of degree P. And not only that, but EF prime over, no, F prime here. But EF prime over F is Galois. Right? This and this, these are the two conditions. This is cyclic of degree P and this is Galois. That's what is being asserted. So I have to show that there's an F prime, which is there. That's the diagram. So here's the proof. First, you take E hat to be the Galois closure of E over F. There is such a thing because E over F is separable by hypothesis, right? Okay, I don't know. Take the Galois closure, take the Galois group. Now, what do we know about this Galois group? We know that it's solvable. Why? By hypothesis on E over F. By hypothesis, when I take the Galois closure, I get a solvable group. But it's also a transitive group. Why is it transitive? Because a Galois group is always transitive in some sense. So it acts transitively on the set of all embeddings of E inside E hat. And there are P such embeddings because this degree is equal to P. And therefore, this gamma can be viewed as a transitive solvable subgroup of SP, of the symmetric group. And what did our lemma say about such things? That if I have a transitive solvable group of the symmetric group of index, prime index P, then it has a unique Silo subgroup of order P. I mean, Silo subgroup, unique Silo subgroup, because the order of the Silo subgroup of SP is, of course, P, right? Because P factorial is the order of this group, and that's P times some P minus 1 factorial, and this P minus 1 factorial is prime to P, right? So it contains a unique group of order P, and G modulo that group, that's a group P, is cyclic of order dividing P minus 1 because it's a subgroup of FP star. Okay. So F prime is what we are looking for. You just take this F prime to be E hat, the fixed points of E hat under the action of the group P. Of course, we have to check that f prime over f is cyclic of degree dividing p minus 1. And that's clear because G modulo P is cyclic of order dividing p minus 1, right? I mean, if you have, what is it? F, and then E hat here, and then this P, so this is going to be E hat P, and this is being called F prime. The group here is P, the group here is gamma modulo P, which is subgroup of Fp star. And yeah, so this is cyclic of degree dividing p minus 1. Now, we also have to prove that EF prime is Galois over F. That's because EF prime is actually equal to E hat. Why? Why is it equal to E hat? Of course, E and F prime are both contained in E hat, and they are linearly disjoint over F, because this is of degree P and this is of degree dividing P minus 1. So when I take their compositum, their degree is going to be the product of the two degrees, but that is also equal to the degree of E hat over P. Because what is, you have E hat P, this is terrible, I'm sorry, I don't know. And this is F, this is P, and this is of course, I'm calling it F prime, so F prime over F. So the total degree of is of course P times F prime over F. That's what I've written. That's the degree of E hat over F as well. Now, so this is contained in this, and they have the same degree, therefore they are equal. And therefore this EF prime is Galois over F, because this is obviously Galois over F by definition. E hat is Galois. Now there's a converse to this. What does the converse say? That if I have a cyclic extension of degree dividing p minus 1 and a cyclic extension of degree p of that f prime, okay, that is what is given to me. And the lemma says that if by any chance L is Galois over f, then there exists a degree p extension E of f. It's going to be solvable such that this L is equal to EF prime. So, so first we had, from a solvable extension of F, we arrived at a pair F prime and L. Where this F prime was cyclic of degree dividing p minus 1, L over F prime was cyclic of degree p, and L over F was Galois. So from one solvable extension of degree p, of course, we got this kind of a pair. Now we are going in the other direction. Given such a pair, given a cyclic extension of degree dividing p minus 1 and a cyclic extension of f prime of degree p, if L is Galois over f, then there exists a degree p extension E of f such that this L is obtained from that E by composing with f prime. Not only does such an E exists, but it is essentially unique up to conjugation by f. That's a lemma. And the proof is similar. This is what is given to you. I mean, this is the diagram. You are given that this G is cyclic of degree dividing p minus 1. This capital P is cyclic of degree p. And this L over F is Galois, so there's a Galois group G, gamma, sorry. And I have this short exact sequence. Let me call D the order of this group G. So this D divides P minus 1. In particular, it's prime to P. Okay, so what's the proof? There's a proof of so this short exact sequence of groups, the order of the quotient is prime to the order of the subgroup. So there is a section, and any two sections are conjugate by an element of the subgroup. Then the image of the quotient under this section is a subgroup of index P. And if I take the invariants under that subgroup, this is going to be an extension of F of degree P. So we have got an extension of degree P. We have to now show that it's soluble, that L is equal to this compositum, and any two such extensions are F conjugate. Right? We have to produce an F having these three properties. We have produced the F, but now it's easy to verify that it has these properties. For example, why is F soluble? Because F is contained in L, and L over F is soluble. Why is L over F soluble? Because this is cyclic, this is cyclic, so the whole thing is soluble. And if something is contained in a soluble extension, then of course it is itself solvable, right? Because subgroups and quotients of soluble groups are solvable. Now, why is L equal to E F prime? This is the same as before. You have E and you have F prime. This is of degree P. This is of degree D, which is prime to P. So they are linearly disjoint, and therefore their E F prime their compositum is of degree P times D, but this compositum E F prime is contained in L, which is given to me, right? Right, L is given to me. And this is of degree P times D. This is also of degree P times D. Therefore, they have to be equal. Why are any two such extensions F conjugate? Because any two sections are P conjugate. So this directly follows from Schur-Sassenhaus. Okay, so I'm now passing to a slightly different thing. So I'll wait for a few minutes to see if there are any questions. No questions? Okay, so let's continue. So let's summarize what we have done. We have a field F and a prime P. We have the set of all soluble extensions of F of degree P. Of course, everything is to be taken up to F isomorphism or F conjugation. And we have put them in bijection with pairs consisting of a cyclic extension of F of degree dividing P minus 1. That's one thing. And the second component of the pair is a cyclic extension of F prime of degree P such that L is Galois over F. So we have established this bijection. Okay. Now, if I let K stand for the compositum of all cyclic extensions of F of degree dividing P minus 1. You see, the slight problem with this bijection is that for every E, if I have an E here, then I get, of course, a pair F. I don't know why this is happening today. F prime comma L, right? Oh, well, okay, let me just say it. This F prime depends upon E. So I'm going to remedy this by taking this K to be the composition of all these F primes. Huh? Yeah, it said here, if I have a solvable extension of degree P, then I get an F prime of degree, yeah. Then EF prime, there's an extension F prime of degree dividing P minus 1, such that EF prime is cyclic of degree P over F prime and Galois over F. All such F primes are contained in K. So EK over K is going to be cyclic of degree P, and EK over K is Galois. Here EK, it's F. This is not K, this is F. Okay, so the difference is that for each E over F, earlier we had an F prime which depended upon this E. But now this K does not depend upon E. It works for every E. It contains every F prime. Yeah, it works for every E because it contains every F prime. I don't know what is happening. This way it's going to be difficult because I want to be able to write with this pen now. Maybe it's not charged or something. It contains every F prime. Ridiculous. Okay. Now, so from degree P solvable extensions of F to degree P cyclic extensions of K, cyclic. Huh? Here the word is cyclic. Here the word is just solvable. So not even Galois, huh? Not necessarily. So I've got this map from E, which takes E to EK, the composition of E and K. So we could ask, what's the image? And here's the proposition which answers this question. It says that the image consists of all those L over K, which are Galois over F. So elements of this are just L over K, which are cyclic of degree P. But that does not mean that they are Galois over F. And the proposition is saying that if something comes from a degree P cyclic solvable extension of F, then those L's are actually Galois over F, right? And it's the same proof as before using Schur-Zassenhaus. But now there's a slight difference because this K over F need not be a finite extension. So when you don't have a finite extension of Galois groups, the Galois group is not an ordinary group. It's what is called a profinite group, right? So it's a projective limit. We discussed projective limits in the very first lecture. So a profinite group is a projective limit of finite groups. And so it becomes a topological group, and the Galois theory works not for arbitrary subgroups, but only for closed subgroups. So that's something which we are going to neglect. We don't really need it so much. Okay. Now, notice that if the characteristic of f is different from p, then this k contains zeta p, a primitive pth root of unity. Why is that? Because f zeta p over f is a cyclic extension of degree dividing p minus 1. And k contains all cyclic extensions of f of degree dividing p minus 1. Okay, so our next question will be that we have this bijection, which is, what is it? Coming from Kumar theory or from Artin Schreier theory, a bijection between the set of all cyclic extensions of degree p over k with fp lines in k star modulo k star to the power p if the characteristic of f is different from p, because k contains a primitive pth root of unity. That's what we have noted here. Or if the characteristic of f is equal to p, not 0, equal to p, then fp lines in this k plus modulo pk plus, where p is our old endomorphism, x to the power p minus x. So now this is Kumar theory or Artin Schreier theory applied to the field k. But now this k is obtained from f, right, by adjoining, it's the maximal abelian extension of f of exponent dividing p minus 1, which is the same as is the compositum of all cyclic extensions of f of degree dividing p minus 1. That's what k is now. And inside this, we have a special subset, which is those extensions L of k, which are Galois over f. Here we are talking of all cyclic extensions L of k of degree p, but there are those L over k which are Galois over f. So that's a subset here. And this, the whole set is in bijection with this or with this. So what does the subset correspond to in this or this? I mean, we have to specify the subset here and the subset here, which corresponds to the subset, which corresponds to this subset over here, right? So here is the answer. So a degree p cyclic extension L over k is Galois over f if and only if the corresponding line D, which is a one-dimensional subspace of k star modulo k star to the power p, or of k plus modulo pk plus, if that line is G stable, where G is the Galois group of k over f. And so assume that it's G stable. Then if G acts on D via some character chi, then G will act on P, the Galois group of L over K, where L is obtained from K by adjoining the pth roots of everything in D, or the Artin Schreier roots of everything in D, via the character omega times chi inverse. Why should G act on P? G acts on P because of this exact, so because of this inclusion here. So this gives rise to the exact sequence P. So if I call this group gamma, then gamma, and this is G here, trivial. And P is commutative, right? Of course, it's not just not just commutative, but it's even cyclic of the. But so whenever I have a short exact sequence with a commutative kernel, the quotient acts on the kernel by conjugation. So you take an element G here and you lift it to some gamma, and then gamma, of course, there's a map from gamma. I mean, it takes little p is a bad notation for elements of this. Because little p is already a prime number. So it takes sigma to this gamma, sigma, gamma inverse. So that's the action. So G acting on sigma is gamma, sigma, gamma inverse. Okay. So let's prove this. The first part, which says that L is Galois over F if and only if D is G stable, which this is something that we have seen earlier as well. And this is when we had a field K, and then we had this field K prime, which is obtained from K by adjoining a primitive pth root of unity, and then we had delta, and then we had delta stable lines, etc. Right? Something which I recalled at the beginning of the lecture today as well. So this part is okay. The second part says that if G acts on the FP line del D via some character chi, then we have to show that this G acts on P via omega chi inverse. That is the question. Here is how G acts on P. And omega is this cyclotomic character. Of course, this is there only when the characteristic of F is different from P. And it's just a trivial character when the characteristic of F is equal to P. There are no pth roots of unity. In my case, no primitive pth root of unity when the characteristic of the field is equal to P. So what is L here? L is obtained from K by adjoining. So I'm going to prove it in this case first. The characteristic of F is different from P. In that case, L is obtained by adjoining the pth roots of everything in D. And this is the short exact sequence which I've already been talking about. This is the Galois group here, which is cyclic of order P. This is the total Galois group, and this is abelian of exponent dividing P minus 1. So that gives you an action of G on P, as I've explained. And we have to show that this action is via omega chi inverse, right? Okay. So D is after all a line. It's generated by one element. I choose an A in K star, whose image A bar in K star modulo K star to the power P generates the line D. Okay. And I extract a pth root of this A, adjoin it to K to obtain the extension L. And I also choose a primitive pth root of unity. That gives me a generator sigma of the Galois group P, the one which sends this particular X, this particular pth root of A to zeta times A itself, where zeta is this particular pth root of unity. And what we have to show is that gamma, sigma, gamma inverse is equal to sigma to the power this thing here. To say that G X on what P via, no, it's omega, not chi, via omega chi inverse means that when I conjugate sigma by gamma, I get this particular power of sigma. Which particular power? This particular power. That's what, yeah. And of course, these are all elements of the group P. And to show that these two elements of the group P are equal, we just have to, it's enough to show that they do the same thing to X. So yeah, we have to show that this applied to X is zeta to this power times X. Okay. And then, and this is what sigma to the power omega chi inverse gamma bar does to X, right? Okay, so let's get going. Gamma bar of A bar is A bar to the power chi gamma bar for every gamma. Why? This is by hypothesis. By hypothesis, Gx on D via chi. That is what is being translated here. Okay. Now, gamma x to the power p, that's gamma of x to the power p, which is gamma of a, because x to the power p is a. Now, these two elements, so this gamma x is a pth root of gamma a. That's what this says. Huh? Gamma x is a pth root of gamma a. But x is a pth root of x to the power p is a, right? So this gamma a and gamma x will have to, I mean, both of them are pth roots of, wait a moment. So how do I say it? Gamma of a. So the conclusion is that this gamma of x, since its pth power is gamma of a, it will have to be of the form b gamma times x to the power chi gamma bar for some b gamma in k. Because gamma of a is a to the power chi gamma. This is right. But I have to choose this b gammas consistently so that you know, when I do gamma inverse gamma of x, I should get x, not 1, of course. I mean, I want gamma inverse gamma to be equal to 1, and therefore gamma inverse gamma x to be equal to x. So in order for them to be consistent, they have to satisfy this condition. Now you just compute. All the analysis is kind of over. The rest of it is just computation. This conjugate acting on x is you first apply gamma inverse to x. What will you get? You will get b gamma inverse, because, and x to the power chi inverse of gamma bar, right? Because gamma applied to x is b gamma x to the power chi of gamma bar. Now, when you, instead of gamma, you have gamma inverse, so that's what you will get. Okay. Now you take sigma also inside, you apply sigma to these things. But sigma doesn't do anything to B gamma inverse because it's in the base field K. But sigma does something to X. Sigma of X we know is zeta times X. But here we don't have X, we have X to some power. So you'll have zeta to the same power times X to the same power. Now you again apply gamma. So you'll have gamma bx, zeta to the power, this was already there. And here is an omega which appears. Why? Because gamma of zeta, so excuse me, gamma of zeta is omega to the power, no, zeta to the power omega gamma bar. That's how omega has been defined. This is gamma here. So I get this omega. And then this is what I get when I apply gamma to X, B gamma times, yeah, normally I'll get X to the power chi gamma bar, but there's already this chi inverse gamma bar, and this will cancel out. So I'll just be left with an X. So, and these two terms, this one here and this one here, they are inverse to, I mean, their product is equal to 1 because I want gamma inverse gamma to be equal to 1. So we have this relation between the B's. And if these two terms give you 1, then I'm left with just this much. And that's exactly what we wanted to prove, that this is the character which gives the action. Okay, so we have proved it in the case when the characteristic is different from P. Now, I have also written it down in the case when the characteristic is equal to P. I'm sure you are convinced, I mean, you anticipate the proof is not going to be any different. The only difference is going to be the shift from multiplicative notation to additive notation. And here it is, it's written out. So I advise you to take a look at it. Or in fact, even better, you just attempt it by yourselves. Just try to imitate this proof from this multiplicative situation to the additive situation, from sort of Kummer theory to Artin-Schreier theory. So, and if you are not able to do it, then you can just look it up here. Now, are there any questions? I have 2 minutes left, so I'm anticipating some questions now. Yeah, are there any questions in the chat box? No. Okay, so if not, let's finish for today and we'll meet on Wednesday.